Hello. In this lecture, we'll first state inverse function theorem. So inverse function theorem, it states the following. So suppose you have a differential map from Rn to Rn. So both the dimension of the domain and codomain space are the same. And suppose the differential of that map is an isomorphism. So then that map is a local diffeomorphism. Means so for each point, there exists a neighborhood of that point such that if you restrict that map to that neighborhood, so then that restriction map, it will be a bijection. It is differentiable, and inverse of that map will be again differential. Okay, so using that, so we'll show that if I take any regular surface in R3, so locally it is a graph of a function. Okay, so let us begin. Okay, so let us take f be a function from u to Rn, be a differentiable function defined on an open subset u of Rn, and now suppose so suppose that at p belonging to u, the differential map, which is a linear map from Rn to Rn, is an isomorphism. Okay, so then, so there exists an open neighborhood P of P such that, so there exists an open neighborhood of B of P and also an open neighborhood W of FP and an open neighborhood W of FP such that, so if I restrict, so this F on B, so it will be a map from B to W, so is a diffeomorphism. So meaning, so diffeomorphism means, so that is F restricted to B is a bijection, and so F inverse F restricted to B, it is automatically it is a differential map because F we have started with a differential map. So inverse of this map, which is from W to B, is a differentiable map. Okay. So we'll be not proving this thing. So if you have done a course in multivariable calculus, so there you have seen this inverse function theorem, proof of this inverse function theorem. Okay, so let me give an example. So let us take, so let f of xy equal to ex cos y, ex sin y. So this f, it is a function from R2 to R2. And it is a differentiable map. Okay, so now note that if I take f x comma y, and if I take f x comma y plus 2 pi, so both of them coincide. So f of xy is equal to f of xy plus 2 pi. Okay, so because of this, so this map is not one-to-one. So this implies that f is not injective. Okay, so f is not injective. All right, so now we want to apply this inverse function theorem. So locally it will be an injective map, and it will be a diffeomorphism, locally diffeomorphism, that we want to show. So in order to do that thing, so you take the differential of this map f at the point xy. So the corresponding matrix of this linear map, it will be what? So it will be ex cos y. So you are taking the partial derivative of this first coordinate with respect to x, and in the second entry, the partial derivative of the first coordinate with respect to y. So if I take this thing, so it will be minus ex sin y. And the second row will be the following. So ex sin y, ex cos y. So this will be the matrix of this linear map. Uh, yeah. So now, so what is the determinant of this matrix? So this is always equal to ex, and this is not equal to 0 for all x. Okay, so this matrix is non-singular. Okay, so this matrix is non-singular for all x. So therefore, so this implies that, so this df xy is an isomorphism. So it is a map from this R2 to R2. So this is an isomorphism. Okay, so now I can apply here this inverse function theorem. So by inverse function theorem, so for all xy in R2, so there exists an open neighborhood Pxy containing this point xy, and an open neighborhood W containing this f of xy, such that, so if I take f restricted to B, so it will be a map from B to W, so is a diffeomorphism. Okay, so in this particular example, also you can find this B and W. So for example, if I take this strip, so let us take, so this B to be equal to this interval. This is in fact R cross 0 to pi. Okay, so if I take this thing, so in R2, it is this strip. Yeah, so this is the strip. So this point is 0, 0, and this is 0, comma 2 pi. Okay, so now if I take any vertical line, so note that these endpoints are not there in this domain. So this might be. So now if I map this under F, so what will be the image of this B? Yeah, so if I take this vertical line, so suppose this is x comma 0, and this coordinate is x comma 2 pi. Okay, so f of x comma 0, so this is equal to e to the power x, again, which is equal to x f of x comma 2 pi. Okay, so therefore and yeah, so here x is fixed here, so note that, so this x is fixed. So I'll get a circle of radius e to the power x. So this point, it will be not there. Okay, and now you vary this x. Okay, so you'll get, so this point, it will be not there. Okay, so what will be my w? So w will be equal to, so R2 minus this, so x comma 0, where this x is greater than equals to 0. So this non-negative side of the x-axis, it will be deleted. So that is my w. Okay, so f is, now it is a map from this B to w. So this is a diffeomorphism. Okay, so now let us take a regular surface in R3. So we want to show that using this inverse function theorem, that it is locally, it is a graph of a function. Okay, so proposition. Yeah, so before again proving this proposition, so let me state this thing. So suppose you take this sphere. So this is my sphere. So this is not a graph of a function. Okay, so now if I take any small surface pair, something, maybe something like this. So this part, it is a graph of a function. Okay, and similarly, if I take this part, this small patch, So this again small patch, it will be a graph of a function, something like this. Okay. So in general, so this is true. So let us take a, so let S be a regular surface in R3. Okay. And so let us take, so let P be any arbitrary point in S. So then, so there exists an open neighborhood B of P in S such that, so this B is the graph of a function of a differentiable function uh, which has one of the following three forms. So z equals to fxy. So y equals to gxz, or x equals to hyz. Okay. All right. So what is the proof of this? Okay. So let U sigma be a surface patch such that, so this P, it belongs to sigma U. Okay. So now if I take, so sigma of UB, so sigma, it is a map from this U to R3, so it will have three coordinates. So X UB, comma Y UB, comma Z UB. Okay. So we have this three coordinates. And now let us take the matrix of this T sigma. Yeah. So the matrix will be, so XU, XB, YU, YB, ZU, ZB. So this is the shorthand notation of partial derivatives. So XU means del X del U. XB means the partial derivative of X with respect to B, and so on. Okay. So now this S is a regular surface. So this means that, so this T of sigma at the point UB is injective. Okay. So this means that, so rank of this matrix, so rank of the matrix of T sigma UB is 2. Okay. So rank of this matrix is 2. So now if I take this minor, So one of this minor, so which is denoted like this. So del xy del ub. So this is xu, xb, yu, yb, and take the determinant of this, and del yz del ub. So it is again the determinant of yu, yb, zu, zb, and we have the third thing. So del zx del ub, determinant of zu, zb, xu, xb. So one of these minors will be not equal to 0. So one of the minors is not equal to 0. Okay, so let us assume, so let del xy del ub, so this is not equal to 0. Okay, so we have assumed that thing. So now let us take this function. So pi is this projection map. So you're projecting to the xy plane. So pi of xyz. So this is x comma y. Okay, and so now you have this function. So u to R3 to R2. So pi is a map from R3 to R2, and sigma it is a map from u to R3. So you take the composition map. So pi compose sigma, it is a map from u to R2. Okay, so pi compose sigma of ub. So this is x ub comma y ub. All right, and so the differential of this map at the point ub. Okay, so because we have assumed this thing, so differential of this map, so this will correspond to this matrix. Yeah, and so determinant of this is not equal to 0. Okay, so that we have assumed. So this means that, so this differential is an isomorphism. Okay, so now we can apply inverse function theorem on this map pi compose sigma. So apply inverse function theorem on pi compose sigma. Okay, yeah. So then so what we'll get, so we have started with this point p, and we want to find a neighborhood of this point p. Okay, such that so z will be equal to your fxy. So that we want to find on this neighborhood. Okay, so let us see. So by applying inverse function theorem, so what we'll get? So there exists an open neighborhood V of P such that so pi compose sigma restricted to B2, again image of this map is a diffeomorphism. Okay, so this will get so here one small mistake I have made. So there exists an open neighborhood. Let us take B1 of Q, so which is nothing but sigma, so Q, so where this sigma of Q equal to P. Okay. So there exists an open neighborhood B1 of Q such that pi compose sigma restricted to B1 to this thing pi compose sigma B1. So this is a diffeomorphism. Okay, so note that again I can draw a picture. So this is my U, and the sigma it is a map from this U to R3. So the image is something like this. So this is my sigma U. So P is contained in sigma U, and Q under sigma it is going to P. All right. So this is a diffeomorphism, and let us take, so let B to be equal to sigma of B1. Okay. So then B is an open neighborhood of P. Okay, so then B is an open neighborhood of P because we have taken the sigma to be a homeomorphism. Okay, and yeah. All right, so maybe I can just draw the picture here. So I have this B1 now, so which contains the point Q, and it is going to this surface patch. So this is my sigma of B1, which is equal to your B. Okay, and then you are taking the projection. Okay, so then you are taking the projection. So yeah, so this is my pi. So if I take this thing, so this is, so if I take this projection, so this will be pi compose sigma of B1. Okay, all right. So therefore it is clear. Now here it is a, so this picture, it is graph of a function of some function fxy. Okay, so pi compose sigma inverse. Okay, so this is a, now it is a map from, so this xy, so this is equal to uxy comma bxy. Okay, so if I take any point xy here, okay, So this will first go to here and then go to here. Okay, so B1, it is a subset of R2. Okay, so XY under pi compose sigma inverse, it will go to UXY, comma VXY. Okay, and so now let Fxy equal to the Z UXI, comma VXY. Yeah, so what is this ZUXY, comma VXY? So note that this sigma, so UB, it is X UB, Y UB, Z UB. Okay, so now this U, again, it is also a function of XY, B also it is a function of XY. Okay, so therefore this F of XY, so this is equal to Z of UXY, comma BXY, where this XY, now it belongs to pi compose sigma B1. Okay, so therefore, therefore we have shown the theorem. So locally, it is a graph of a function. So this surface is a graph of a function. Okay, so here we, so suppose you take the surface patch. So what we have shown, so I am getting a point here in this case. So this patch is graph of a function. Okay, so this is z equals to fxy. So coordinate of this point is xy, comma fxy. Okay, so here this xy is varying here. Okay, so therefore we have proved the theorem. So we'll continue in the next class.